Welcome to BakoMaths, and today's lesson we'll be looking at conjugates of complex numbers. And if you haven't subscribed to this channel, kindly subscribe and hit on the notification bell so that when a new video is being published, you are going to be the very first person to be notified. Now let's start. So we are talking about complex conjugates. This is what we mean when we talk about complex conjugates. If you have a given complex number z, which is equal to a plus bi, then the conjugate of this complex number is given as z bar. So the z bar here means that the conjugate of the complex number z. Now, this conjugate is written as the reverse of the sign of the imaginary part of the complex number. So the complex number is a plus bi. So the reverse of the sign of the imaginary part now becomes a minus bi, and that becomes the conjugate of the complex number a plus bi. So you are talking about a minus bi being the conjugate of the complex number a plus bi. Why? Because when you talk of complex conjugates, then we are interested in changing or reversing the sign of the imaginary part, and that is very simple. Geometrically, we can represent the complex number and its conjugate on the complex plane. So if you have the complex plane as this, then it means that for the complex number z equals pi, so on the real axis, so we have the real axis here, and then also have the imaginary axis here. So representing it on the real axis, then z will be of this form or will be at this side. So we have our z, which means that our z is equal to a plus bi. And then our z bar, like you said, the reverse of z becomes z bar, which means our z bar will now be at this side, which means our z bar now is equal to a minus bi. So beautifully, this is what we can represent. This is how we can represent it on the complex plane. So well, we can equally join them, and we have something like this. So this is how we can geometrically represent the complex number and its conjugate on the complex plane. So in polar form, we can represent z plus bi as a comma b, and then you can also represent a comma minus b as the conjugate of it. So this is what we mean when we talk about complex conjugates. Now let's take an example on complex conjugates and see how best we can analyze and solve them. For example, one says that find the conjugate of the following complex numbers. Z is equal to 3 plus 2i. So with this, we have the question as z to be equal to 3 plus 2i. So that is z. So its conjugate z bar will be equal to, as the opposite sign of the imaginary number. So 3 minus 2i becomes the conjugate of z equals to 3 plus 2i. Now let's go to the next example. Have the solution here, and you want to find the conjugate of minus 4 minus 2i. So just like we said, reversing the sign of the imaginary part of the complex number and adding it to the real number becomes the z conjugate. So z conjugate now is equal to minus 4 plus 2i. So minus 4 plus 2i now becomes the conjugate of the complex number z is equal to minus 4 minus 2i. Now let's try the next set of examples as well. So you have C here, I want to find the conjugate of this. So z is equal to I. So once you're interested in negating or changing the sign of the imaginary number to its opposite sign, that means you have z to be equal to minus I. Now let's try the last example here, and we want to find the conjugate of the complex number z is equal to 4. So for z conjugate, then we are saying that we are going to reverse the sign of the imaginary part. And here there is no imaginary part here. So it means that z conjugate is going to be the same thing as 4 here, because our focus is on changing or reversing the sign of the imaginary part. And that is Now let's try the last set of examples for today's video. So this happens to be the last example, and we are saying that for any complex number z, prove that the complex number z and its conjugate being multiplied is equal to the magnitude of the complex number squared. So this is what we want to prove for. So solution here, we are saying that if z is a complex number, then it should be equal to a plus bi. This is what we mean when we talk about a complex number. And you are saying the conjugate of z, which means z bar is equal to a minus bi. And you want to prove that when we multiply the complex number z and its conjugate, we are going to get the magnitude of z squared. This is what we mean. Now, let's take it from the magnitude of z. When you talk about the magnitude of z, they are talking about the modulus or the length of the complex number z. And that is equal to the square root of a squared plus b squared. That becomes the magnitude of z. So now, if you are saying the magnitude of z squared, then we should also square that of square root of a squared plus b squared, which means z magnitude here is equal to z magnitude squared is equal to that is, this square takes away the square root sign. You are left with a squared plus b squared. So this is what we want to prove. We want to prove that when we multiply z and z bar, we should get a squared plus b squared. Now let's tackle it. So once you have been able to analyze it, then you are saying that z times z bar should be equal to z magnitude squared. What is z? Z we know to be a plus bi, and z bar we know to be a minus bi, and it should be equal to z magnitude squared. Now we ask ourselves, how do we multiply this? So it follows the normal FOIL method, which means a multiplies a, we have here as a squared. So a multiplies a, we have here as a squared, and a multiplies minus bi, we have minus abi, and a multiplies plus bi, we have a plus bi. Now bi multiply minus bi, then we are going to get minus b squared I squared, which is equal to the magnitude of z squared. So here we can see that the negative abi take away the positive abi, and we are left with a squared minus b squared I squared, which is equal to the magnitude of z squared. So here we can see that when we consider I squared, we are saying that for every I squared in complex numbers, its value here is minus 1. So we do that substitution here, which means our a squared here minus b squared, now multiply by minus 1, that is for I squared, is equal to the magnitude of z squared. So here we can see that a squared maintained, and minus b squared multiplied by minus 1, here we have plus b squared, which is equal to the magnitude of z squared. So just like we have proven here, therefore we can say that the magnitude of z squared is equal to a squared plus b squared, hence proven. Just like we elaborated earlier on, we have been able to prove that for every z squared magnitude, its value is a squared plus z squared, and that is exactly the same thing as we have here. So we can conclude by saying, hence, for every complex number and its conjugates, then we are going to get the magnitude of the complex number squared. So this is all about the proof here. We end today's video. and we appreciate you for watching. So thank you for watching. Kindly like, you comment, subscribe, and share. Remember that this is BakoMaths, thinking beyond infinity.